So I'm going to present a localized hybrid simulation of Martian crustal magnetic cusp regions and talk about the influence on ironscape. So Mars has these localized crustal magnetic fields which can interact with solar wind and IMF and create a very unique hybrid magnetosphere. Crustal magnetic cusp regions refer to where the field lines are mostly vertical and open, with one end connecting to the ionosphere. And there can be various physical processes happening in these cusp regions, like particle precipitation, field line currents, and ion outflow. And usually auroras are also associated with these regions. So we will need a localized model with high spatial resolutions and ion kinetics to understand these physical processes. So we plan to use a localized hybrid model to study the electric potential structure and the particle transport and ironscape in the cusp regions. So as you all know, that hybrid model tracks ions as particles and treats electrons as massless neutralizing fluid. We use the hybrid simulation platform developed at the Finnish Meteorological Institute. We apply this model to a cusp region on the night side of Mars above the exobase with moderately strong cusp magnetic field, which is about 100 nanotesla at the bottom. Since this is a symmetric system, to make the model run faster, we use a 2D simulation domain and with periodical boundary conditions in the third dimension. There are two plasma populations in this simulation. One is a tenuous, hot, and fast-moving plasma, magnetospheric plasma represented by proton ions coming from the upper boundary. The other is a dense, cold, and slow-moving ionospheric plasma represented by oxygen ions injected from the lower boundary. And also to avoid any artificial effects from the boundaries, we only look at the model results within the smaller region in this yellow box. So we run the model until everything converges. These are the results of the electric field and the current density distribution in the vertical plane. First thing you will notice is probably that the electric field are mostly pointing upward. And if you look at the vertical axis in the central cusp region, this upward electric field produce a potential drop, which is about 6 volts for this case. This is small, but this is enough to remove almost all heavy ion species from the ionosphere. And also, if you look at the different terms of this electric field in the generalized Ohm's law, you would see that the most significant contribution to this vertical potential drop is from the Hall term, which is the J cross B force. And also, if you look at the current density, we do see these strong field line currents in the cusp region. So this model can at least qualitatively reproduce the potential drop and the field line currents in the Martian crustal magnetic cusp region. And also the vertical electric potential drop is dominated by the J cross B, or the Hall term in this case. So if we look at the particle distributions and the transport from the model, first, this is the magnetospheric protons coming from the upper boundary. If you look at their velocity, you can see that they are significantly decelerated in the central cusp region, and their density becomes higher in this region. For the ionospheric ions, the oxygen ions coming from the lower boundary with very small velocity, you can see they have been accelerated to up to 20 kilometers per second, and they are removed from the central cusp region. Although this model does not physically track the motion of electrons, but we can calculate the electron velocity. And if you look at this electron velocity, you can also see the electrons are being accelerated downward into the cusp region. And these electrons carry the field line currents pointing upward. So how does this system build up? When you have the magnetic field distribution in the cusp region like this in the vertical and the horizontal plane, and when there is a downward ion flow, these ions feel the Lorentz force, which is pointing into the vertical plane on the one side and pointing out of this plane on the other side. And the electrons will feel the force in the opposite direction. And this will form a current loop in the horizontal plane. And this current loop is, we do observe this current loop in the model results. And this current loop will generate a downward pointing induced magnetic field. We also see this from our model results. And this induced magnetic field is much weaker comparing to the background crustal field. So it does not really change the morphology or distribution of the magnetic field much. So in this cusp region, when we have this current horizontal current loop and a magnetic field distribution like this, it will generate a upward pointing J cross B force, and this dominates the upward electric field we saw in the model, and this also drives a strong field line currents in the central cusp region, as we see in the model, and these field line currents in the central cusp region will then generate a loop-like induced magnetic field in the horizontal plane. Also, we see this feature in the model too. And all these are just very rough zeroth order analysis. From the model results, you can see that the system itself is actually much more complicated with many fine structures and different layers too. But the point I want to make here is that this dominant downward ion flow and the cusp field distribution are the two key factors to generate the horizontal current loop and the upward vertical electric field. And this vertical potential drop represents the energy and momentum transfer between the two plasma populations, which is made through the magnetic field, also the buildup of the current and the J cross B force. So next, we run this model with a few different inputs, different crustal magnetic field and different ionospheric plasma densities. First, we notice that if we change the crust field strength, this potential drop does increase significantly with the crustal field strength. This is straightforward because when you have stronger crust field, you will get a stronger J cross B force, and which means stronger crust field can make the energy transfer between the two plasma population more efficient. Excuse me. And if we change the ionospheric plasma density Ni here, we see that the potential drop does decrease significantly with the ionospheric density. This is also easy to understand. When you have more ionospheric ions moving upward, you actually get a weaker net downward ion flow, which means a weaker horizontal J current loop and a weaker upward J cross B force. Or if you like to think in the way of energy transfer, when you have the same energy input from the magnetospheric plasma and it's shared among more ionospheric ions, so each ionospheric ions get less acceleration. And also for this for this dense ionosphere case, we found that the ambipolar electric field becomes more dominant. And I think the question everyone here is mostly interested in is that is the ionscape in the crustal magnetic cusp region increased? So this really depends on what exactly is this magnetospheric plasma. In the model, we call this magnetospheric plasma, but the model itself doesn't really care the source or the origin of this downward plasma flow, as long as it is a downward plasma flow. So if this downward plasma flow is mostly composed of solar wind ions, then of course it will increase the escape of planetary ions from the cusp region. However, if these downward plasma flow are returning planetary ions, then it's more complicated. It depends on what species are the returning ions and what are the spatial distribution of the returning ion fluxes. For example, if the returning ions tend to be one specific species like protons, it will increase the escape of other species of planetary ions like heavy ions. And also if these returning planetary ion fluxes are not specifically associated with Cusp region, it randomly occurs everywhere. So comparing to those region without a Cusp field, in the Cusp region, because of the buildup of potential drop, it does increase the escape of other ionospheric ions. But if these if these returning ion fluxes are associated with the Cusp region, then we cannot really say that the ionscape in the crustal magnetic Cusp region is increased. So in summary, although the crustal magnetic cusp serves as a channel for the energy input into the ionosphere, whether the ionscape in this region is increased really depends on many other factors too. I think I'll leave my summary here and take any questions. Thank you.
Thank you, Yaxue. There's a question in the chat from Eric Lund. How do the field-aligned currents close?
If you can you see my slides here? Okay. If you look at
yes.
Okay, if you look at this distribution of the current density, it does eventually return to the bottom or the lower boundary of this simulation domain. But it also goes out of this simulation domain too, because this is the boundary condition allows the current to flow freely out of the simulation box. So I don't think we can completely answer this question, how does the field-aligned currents closed? But at least as shown in these model results of the current density, some of it does return to the ionosphere.
Thank you. That's a fair point. And one more question from Chuanfei Dong. Yaxue, what did you gain more in this study by using a hybrid peak model compared with a hot MHD model?
I think because this region, if you look at the ion motion, it's not really magnetized. So I guess ion kinetics are really important here. So by applying a hybrid model, it can show the effects from ion kinetics, the kinetic effects from ions better.
Cool. One last question. What is the reason you use O+ instead of molecular O2+ ions, the major species in the Martian ionosphere? Do you expect any significant change of the results for O2+ dominated case?
The reason I used O+ is simply because I wanted to compare these results with the results from a peak model by Andrew Poppe. He used O+ in the very beginning, so I used the same setting as he did. But if I think the point is you really, one is the energy input from the downward ion flow, and if the ionospheric ions are heavier, they require more energy to be accelerated. So I assume if all the other settings are exactly the same, if you have a more heavier species for ionospheric ions, the potential drop would be smaller. But I haven't tried any other ion species for the ionospheric ions yet, but I can try that.